We have already talked about the frequency spectrum of the FM the modulation index, depending on the modulation index. If the modulation index is small, we have a narrowband FM, or if the modulation index is large, we can have a broadband FM. So let's have a quick look at our previous simulations. You see, for example, if the modulation index is small, we have a very narrow band FM. It's like a single peak what we had earlier at the um, with the carrier. Okay, so it's a narrow band FM, so you support the same amplitude carrier. As the modulation index is increased, you see this is one. You have it's again narrow band, but still there is some bandwidth, appreciable bandwidth for an FM signal. So depending on the modulation index, if you increase it 10 folds further, you see broadband FM signal is produced. And if you go on increasing the modulation index again 10 folds, 100, then there's a more range of frequencies that is contained in the spectrum of the FM signal. Okay, so you have more frequencies, and then you have low frequencies, you have high frequencies, and this continuum of frequencies is dependent on the modulating signal, the amplitude of the modulating signal. Okay, so that's what you're looking at the that's how the frequencies, the Chinese frequencies look like, depending on the amplitude of the modulating signal. Okay. Now, analytically, how you look at this is that you have the phase expression, which is the integral of the frequency. Since omega is d phi by dt, then you can write the phase as omega dt. And if you expand the integral, then again this is omega ct. So this is linearly increasing time phase term at the rate of omega c. Then you have another sinusoidally varying phase term, which consists of the amplitude is k oscillator a over omega. It's a constant, and that this term is what constitutes the modulation index. Okay, this is the modulation index. So it's a sinusoidal phase term. It's a sinusoidal phase term being added to omega ct, and phi naught is a constant. So neglecting phi naught and using the usual expansion for cosine a plus b, cosine this is cosine a plus b. So if you expand this the entire term neglecting phi naught, you have cosine, this is a, this is b, so this becomes cosine a, cosine b, similarly minus sine a, sine b. Okay, so these are again cross product terms, and we consider phi m modulation index to be small for narrowband FM spectrum. So if the modulation index is small, it's written over here, if modulation index is small, we have a narrowband angle modulation. Okay, why? How it happens is that you see for small argument of cosine, if you expand the series of cosine, you remember the series of cosine 1 minus x squared over 2 factorial plus x4 over 4 factorial. So the same argument, x is phi m sine a omega t. So it can be expressed as 1 minus x squared over x squared divided by 2 factorial, or 1 minus phi m sine omega a t squared over 2. Same thing like here. We don't need to go any further, expanding it to for the third term or the fourth term. You see x is very small, so this term becomes small because phi m is small. So phi m, or the modulation index, phi m is the modulation index, is small. Okay, it's small. You don't need to expand the expansion for sine or cosine for higher order terms. It's small, so obviously the result is small, so you don't go any further. And similarly, you have this argument over here, so this is only x. So if you see for the expansion of sine, we only consider the first term. You don't need the cube and fifth order terms, and they're small. So well, let's have a look at this expansion. What it implies in transform domain is, so this is the same expression over here. So the first term, look at this first term. The first term is basically a carrier. It's a carrier output. So what you're going to have at the output is omega c over here. Okay, you have a tone at omega c, which is a carrier. So the first term is almost constant. It almost is a constant amplitude spike at carrier frequency, much like an AM signal. So it's not a suppressed carrier, but the carrier comes just like because this is being multiplied by 1 over here. You can forget about this term. Phi m is small. The modulation index is small, so we don't. It's a small term. For the second term, this is sine A, sine B, and this can be expanded in terms of cosines. Okay, so you will have the side bands omega A plus omega C and then omega A minus omega C. So you will have a very small strengths compared to the spike of the carrier. You will have weak strengths of the lower sideband and upper sidebands at omega A. This is omega C minus omega A. Then similarly you will have omega C plus omega A. So this is a very similar spectrum that we have in the AM. Okay, so the bandwidth of this spectrum is twice omega A. The bandwidth is twice omega, just like the AM, okay, what we have discussed earlier. So this expression is just like an AM expression in the transform domain, except that you have weak strengths of the sidebands because your modulation index is small. So this differs from the AM, okay, in two ways. One is that the sidebands are equivalent to having multiplied the audio signal not by cosine but by sine. Okay, so you multiply the sideband with a sine, not by cosine omega t. Note also that in this limit, so the small modulation index, the amplitude of the sideband is small. The amplitude is small because modulation index is small. So the rest of the spectrum stays fixed at 2 mega A. So it's fixed at 2 mega A. All right, just like AM. So that if the modulation index is small, as you've seen previously, if the modulation index is small, your the spectrum is the narrowband FM. Okay, it's just like an AM, so it's still narrowband. But as you increase the modulation index, your deviation increases. If your deviation increases, well, you're comprising of your FM signal comprises of more frequencies. The bandwidth is more. So obviously, this is expected. You will have a broadband FM. Okay, you will have a broadband FM. Okay. So exactly what happened in wideband FM? You look at the equation again for the FM signal. Okay, these are cross product terms over here. Now we see that the signal consists of the products cosine and sine being multiplied by cosine of sine function and sine of sine functions. So when the modulation index is not small, these products are similar and each consists of lower sidebands around omega C with frequency component spaced from the carrier by integral multiples of omega A. You see, since you have the cross product multiplications over here, again around omega C there will be sidebands. Okay, the nature of the sideband is such that the frequency component will be spaced from the carrier by an integral multiple of omega. Well, one way to understand this is if you consider the Bessel functions or the expansion of harmonics of the audio frequency, the Bessel functions. But these functions are usually tabulated. An easy argument is to look at it in terms of deviation. Okay, how much deviation you have. For example, if phi m is large, of course you'll be looking for a more deviation. So the other way of looking at this problem is that referring to the same equation, in time equal to 1/4 of the audio cycle. So for example, this is your audio cycle. Okay, this is your audio cycle, and for 1/4 of the cycle, this is 1/4 of the cycle. Okay, this is, and then this goes on. You see, it's like this. That's the complete cycle. So we are looking for 1/4 of the cycle. This is capital T by 4. All right, this is 1/4 of the cycle. So in 1/4 of the cycle, the phase difference that is produced is phi m. Why? Because after 1/4, sine goes to maximum of its value 1. So the change is phi m radians. Okay, so the change is phi m radians. So the phase of the baseband modulating signal changes by phi m radians, right? And same goes for here as well. The argument is phi m sine omega t. So after a quarter cycle of sine omega t, the phase change is phi m. The phase change is phi m. All right. Now dividing this phase change by the corresponding time interval. The time interval is 1/4. FA being the frequency of the audio signal. Now if you multiply this by pi over here and you multiply this pi over here, well, you have the same expression. Okay, so 2 pi fa is omega a over here, then you're left with the 2 over here, and then there is a pi in the numerator. Okay, all right, here. So that's your actually that's your time interval. So if you divide this space by the time interval, by the quarter time interval, this is the quarter time interval. The average sideband frequency in radians per second is this much. All right. So we are dividing pi of m by this expression over here. All right. We divide this by pi divided by twice omega a. So this expression is the same over here, right? And this is, since this is pi is in radians and this is seconds, so this is radians per second. Okay, radians per second is the frequency where the phase change is phi, right? Now substituting for phi, which is the modulation index, which is the definition of the modulation index, into this expression yields a similar expression that we've seen earlier. This is 2k oscillator a over pi, where 2 over pi can be taken out, and this is the deviation. That's how we defined the deviation before as well. So the deviation is k oscillator a, right? I mean, we have defined this. Hang on. So you see over here, that's your deviation, right? The oscillator VA is defined as deviation in radians per second. So over here, by the same argument, you can write this frequency, the average frequency, as 2 over pi into deviation. So as deviation grows, as the deviation is large, if the modulation index is large, obviously the modulation index is deviation divided by omega a. So if your deviation is large, omega m is large, then the one-sided bandwidth of FM signal when the modulation index is large is roughly equal to the maximum deviation, and the full bandwidth is twice the maximum deviation. Obviously that makes sense, because as the deviation increases, the FM signal comprises of a larger bandwidth consisting of more frequencies. Therefore, it results in a broadband FM. So if you have a larger modulation index, pi m, then over here, if you have a larger modulation index, of course, then you have a broadband FM. So if the deviation is reduced, the bandwidth goes down proportionally at first, but then in the narrowband regime, it stays constant. At twice the audio bandwidth as shown before, just like for the AM case. Okay, so if you have a small modulation index, you are looking at a narrowband FM, and that narrowband FM in the limiting case looks like just an amplitude modulated wave.